So in this video, I'll be talking about overview of statistics and sampling techniques. So we're going to start with the data. So there are two types of data. We can have the qualitative data or a quantitative data. This time we're going to focus on the quantitative part. So for quantitative, there are two. It can be discrete or continuous. So for discrete data, these are data that can be counted or countable data. Like for example, there are 5 kids, so you can just simply count the number of kids. And for the number of workers, you can just simply count them. So for example, there are 96 workers, so you can just count them from 1 to 96, and like 1, 2, 3 laptops. But for continuous, you cannot just simply count them. You need some measurements or instruments to measure them. So for example, you have 3.25 kilograms. So usually the continuous data involves decimals, while discrete, you cannot count directly the decimals. So that's why these are whole numbers. So for continuous data, like for example, 3.25 kilograms, you cannot count it, but you need to measure it using weighing scale. 1.32 miles. So you cannot just simply count it with by your fingers. You need to measure it. 725 inches. All right, so you need a tape measure or whatever instrument to measure it. You cannot just simply count it. Those are continuous data. But usually what I do is just knowing if it involves mostly a variety of data that involves decimal. Especially if it involves decimal, it's a wide variety of data. That's continuous. That's much simpler for me in knowing whichever is continuous or a discrete. But basically, discrete can be counted by fingers. So next is the levels of measurement. So there are 4 levels of measurement. The first is nominal. So if the data can only be used for categories or grouping, then those are what you call nominal. Like for example, color, so red, blue, green, you can arrange them in order. You don't know which one is bigger than the other. So just for grouping, that's nominal. Or the sex, male or female. So you cannot arrange them in order. So that's nominal. For ordinal, they are similar to nominal. They usually can be categorized, but there is ranking. You can rank them like grade level, first, second, third, and fourth. They can be used for grouping, but you can also rank them. You know that fourth year is greater than the third year. The third year is higher level than the second year, and so on. So that's ordinal data. For interval, these are already continuous data. They are a wide variety of values, interval, and also ratio. These are continuous data. These are usually involving decimals, unlike the ordinal and the nominal. Now, the only difference between interval and ratio is the interval, the 0 doesn't mean nothing. Like temperature means temperature at 0 means there is still temperature, but it's just cold temperature, 0 degrees Celsius or Fahrenheit. But for ratio, 0 means nothing. It doesn't exist, or there's nothing in that value. Now, for example, weight, if your weight is 0, so that means you didn't exist at all. Or height at 0, or whatever, anything that has a 0 measurement. Like for example, the weight of milk in milliliter or liters, if it's 0 ml, it means it does not exist at all. So 0 means 0 or nothing in ratio. Next is we are going to talk about the 2 different types of statistics. We have descriptive statistics and inferential statistics. So descriptive statistics is just basically describing the data. You cannot conclude anything, or you are not predicting anything. So just for example, here we have 30%, 20%, and so on. So you can just describe which one is in majority, but you can conclude with that information. While in inferential statistics, as you can see in the illustration, it involves on a normal curve. A normal curve is being used to predict a data. So having a sample and you want to predict what is the result if you do this the same with the entire population. So for predicting is inferential statistics, for describing is for descriptive statistics. So let me illustrate to you the overview of statistics using this diagram. We have descriptive and inferential. So there are two types of statistics. And this under descriptive is measures and frequency distribution. So under the measures, there are three. We have measures of center, measures of variability, and position. So those are the different ways to describe a data. Its center. The variability is about the spreadness of the data, and the position will tell you where the data is being positioned, either in the middle or in the 3/4 or in the 1/4 of the data. While frequency distribution will tell you what percent or what's the majority of the data is. For inferential, it's as I said in the previous slide, it is used for predicting. So there are two types of inferential. These are parametric tests and non-parametric. So parametric tests are the much more accurate statistical tools, but there are a lot of requirements, or we call it assumptions, to follow. While in non-parametric, in majority, it is less accurate, except for some non-parametric tests. But they usually, not all, but they usually change the data into ranks. They are alternatives in case it is not possible for you to follow the assumptions of the parametric tests. So let's have first the parametric. There are two types. We have first the difference. So for testing difference, we have some examples, t-test, ANOVA, and COVA, but there are still a lot of statistical tools under this. For testing relationship, we have some few examples here. We have correlation, like the Pearson's correlation, regression, and covariance-based structural equation modeling. So for the non-parametric, there is also a version of difference and relationship. So for test of difference, we have the Mann-Whitney test, Wilcoxon-Signed-Rank test, and the Kruskal-Wallis test. So the Mann-Whitney test is like the non-parametric version of the t-test for paired samples, if I am not mistaken, and Wilcoxon-Signed-Rank for independent, and for Kruskal-Wallis test for the ANOVA. That's the non-parametric version of the ANOVA test. While for testing relationship, we have some few examples here, like Spearman's Law and Kendall's, both are testing correlation. They are both non-parametric. But as I said, we only use the non-parametric at the last alternative because these are changing the data into ranks, so it is a little less risky to conclude. While we also have some testing relationship for chi-square and PLS-SEM. Chi-square, it doesn't have a version of parametric test. It doesn't change the data into ranks. So this is an exemption. But it's still considered a non-parametric, but we use this because it doesn't have a version of its parametric test. It tests the relationship of two categorical data. While the partial least square SEM, or structural equation modeling, it is considered non-parametric because it doesn't require normality, but it doesn't change the data into ranks. So you don't worry using the PLSM. I would suggest still to use the covariance-based SEM if you meet the requirements or the assumptions, like the normality, like the number of samples, because you need a lot of samples. But for PLSM, it only needs around 80 or closer to 100. You don't need to have a very large sample size, and you don't need to have a normality test for the PLSM. It will still give you accurate result, but as I said, I would still suggest to use covariance based as long as you have met the assumption. Now let's move to the difference between sample and population. So it's very obvious for that the sample is just coming from the population. You just select randomly or non-randomly from the population so that it won't be very expensive and time consuming to collect data from the entire population, because usually population is very big and it's going to be costly. Now, using your sample, you are going to calculate the data from the sample and then infer or predict what will be the result if you are going to do it to the entire population. So you don't need to collect the entire population data in order to get a conclusion. You just need a sample and use the appropriate statistical tool. Next is we're going to talk about sampling techniques. So these are the different ways to collect the data, or we call it sampling. So there are two types of sampling techniques. We have random and non-random sampling. So for random sampling, it's very important to use this if you want, but of course we want to use the parametric test because it's one of the assumptions that the data should be randomly collected. But usually in qualitative studies, the non-random sampling is being used, and we're going to talk about those both sampling techniques. Now we're going to have first the random sampling. So we have first simple random, or we call it fishbowl method, because every participant has an equal chance to be selected. So it's called fishbowl because we're going to use a fishbowl and put the names on there and then draw lots. So that's simple random sampling. So we also have stratified sampling. So it's using subgroup sampling. That means you are dividing the groups into different subgroups and then collect data proportionally. So if you say proportionally, the bigger the subgroup, the more samples that you collect from them. And then we also have cluster sampling. It's called group selection. So you are not selecting only participant but the entire group. So you randomly select the entire group. So if there are 5 groups, you are going to draw lots from those 5 groups, and the selected group will be all the participants in that group will be included. And then we also have systematic sampling. It's called interval selection, where you are going to set an interval. Like for example, let's say 3 as your interval. So every third person that you see in the target population, then that will be part of your participants. So that's kind of random sampling. Every third person, when you count them, that's part of the participants. Now let's move to non-random. So for quota, so we have fixed quotas. So what does it mean by that? So there's a fixed number that you assign. So for every group of participants, if they are divided into groups. So let's say, for example, if there are 5 groups, then you assign quotas. Let's say 10 people for every group. It doesn't matter whether the group is bigger or not, as long as there is a fixed quota, and then you don't select them randomly. You just select whoever is available, and as long as you reach the quota. Now we have purposive sampling. This is also non-random. This is criteria based. So for example, if your study is about to test whether your product for making the hair shiny, then you select participants which are having long hair. So that's what you call purposive sampling, because you select according to the criteria. Your criteria is they must have a long hair. So that's purposive sampling. You don't randomly select them. You are intentionally choosing them because of the criteria you have imposed. Another one is snowball. It's called chain referral. So, for example, you are going to you have to start with one participant. Usually, this is being used when the study is very confidential. Let's say, for example, your study involves a very rare disease, and you are going to ask that participant after interviewing him or her to you're going to ask if he or she knows somebody with the same case so that you can continue the interview with other participants. So that's what you call snowball sampling. That is non-random. And then last is convenience sampling. It is another term is easy access. So whoever you see who is available, then you just select him or her. You don't need to randomly select or look for somebody else if somebody is right here there in front of you. So that's convenience and that's non-random. Now let me teach you how to compute the sample size using Cochrane's formula and also later using the Taro-Yamana's formula. So there are two steps for Cochrane's formula. First is to use this formula, n sub o is equal to z squared times pq over e squared. So what's z? Z is the level of confidence. Usually it's 95%, and the equivalent z for that is 1.96. While the P is the proportion of the population. Usually the P and Q are both 0.5 or 50%. And the E squared is the margin of error. It's usually the 0.05 or 5% margin of error. So those are the common values for Z, P, Q, and E. After computing, you are going to use the value that you got in n sub o in the next formula. N sub o over 1 plus n sub o minus 1 over the population size. So you're going to substitute there, and the capital N, you're going to replace it with the actual population size in order for you to get the suggested sample size using the Cochrane's formula. Now the good news is we have some sample size calculator where you don't need to manually compute using the Cochrane's formula. So we have Rausoft calculator. I believe this is free online. It is using the Cochrane's formula. So we have some boxes that we're going to fill in. So this first box is actually the margin of error, or E in the formula. You just put there 5% because that's the common margin of error. And for Z, you put there 95% level of confidence, or meaning how confident you are that you're gonna have the accurate result. And the N, or the third box, is your population size, the size of the entire population of your target participants. While the P is usually 50% if you don't know the proportion of your participants' characteristic, so that you'll get your sample size. So the recommended sample size according to the Cochrane's formula using the Rausoft calculator is 377 in this example, considering the population size is 20,000. But this sample size is just the minimum. You can have more than that, but you cannot go below this recommended sample size because it will not be valid anymore. Now, another way to compute the sample size is the Taro-Yamana's formula, or previously commonly known as Slovin's formula. So, in 1967, there is a book published that contains this formula, n over 1 plus ne squared. So this is just coming from the Cochrane's formula, which is being simplified. So the n there, or capital N, is the population size. So just input the population size and also your margin of error, commonly 0.05, or the 5% margin of error. And then you will get directly the value using that formula. Unlike the Cochrane's formula where we have some other variables. That's why we have this, which is still coming from the Cochrane's formula, just being simplified. Now, if you don't like to manually compute the Taro-Yamana's formula, so we have some online calculator for using this formula, which is I have found a class gist, if I am correct with its pronunciation. You just need to input your population size. The margin of error is already there. It's 0.05. It's fixed. Then you can get right away your sample size. As I said, sample size calculated from this formula are just minimum. You can go beyond that, but you cannot have below that sample size. Now, commonly used sampling technique is the stratified random sampling, because it is very fair with having sample size being distributed for every um, target area with having different population sizes. So in this example, we have 5 schools in this district, and every school is having different size of population. Some are 170, there is 250, there is 330, 170. So you cannot just simply distribute the samples evenly because they have different sizes. As I mentioned in the previous slide, stratified sampling is collecting the samples proportionally based on the size of each stratum. So to compute first the sample size, we use the Taro-Yamani's formula. We have n over 1 plus n e squared. So we put the n, since our total population size is 930. So we substitute it there, and for the e is 5% or 0.05. Now we compute the bottom first. We have 1 plus 930 times 0.05 squared. Approximately it's 3.33. And then we divide it. We will come up with a decimal. It's 279 point something, but we always round up. No matter how small the decimal is, 279.1, for example, you still round it up because that 0.1 is one whole person. We're talking about a person here, so it's considered one whole, even if it's only 0.1 or 0.01, as long as there's extra point something, you round up. So the minimum sample size now is 280. So how are we going to distribute this 280 to each school? So what we're going to do is to get first the percent or the percentage for each school. So we're going to have 170, that's the population size of that school, divided by the total, which is 930, times 100 in order to get the percent. So it will be 18. So that means 170 is 18% of the total population. Next, 250 divided by 930 times 100. So it will be 27%. 330 divided by 930 times 100 is 35. For 100 divided by 930 times 100, it is 11. And 70 divided by 930 times 100 is 8. So it must be having a total of 100. Now, if you add this all, since you round off into whole number, it's possible to have less than 100 or more than 100. It can be 101, or sometimes like this, it's only 99. Because you're rounding off, sometimes you don't get exactly 100. So in this case, for you to have an exact 100, you can just adjust your values of percent, and that's fine because that's normal since you round off and you don't get 100%. So you just adjust it. So I'll just choose the bottom, which is 9, which is 8, so I'd make it 9 to make it a total of 100. Now, after getting the percent, then we move to the next column, which is for the sample. So we're going to distribute this 280 for each school. So for the first school, since the percent is 18, so we're going to have 280. That's the total population, sample. 280 times 18 divided by 100. So it will be 51. So that means in school 1, out of 170, you can just collect 51. That's the minimum. But as I said, that's the minimum. You cannot have lower than that. So 280 times 27 divided by 100. So the sample size will be 76. So out of 250, you may collect only 76, but you can have more than that, but not below than 76. We have 280 times 35 divided by 100. So it will be 98. 280 times 11 divided by 100 will be 31, and 280 times 9 divided by 100 will be 26. This should be having a total of 280. Now the problem is the total is more than that because of the percent being rounded up. So what you can do to make it fixed with 280, although it's technically fine to have a more than the sample size because it's 282, but for it not to be questioned because of being having different values from the calculated sample size, you can just adjust, but make sure that you don't remove this extra two to just one area. So you have to distribute it from other schools. But since it's only two extras, you can just select two schools. So I just select school 4 and school 5 to make it both subtracted by 1, and so that the total will remain 280. So that's it. So that's how you compute the sample size. So as I said, you can have uh, the minimum for each school, but you cannot go below that, or you cannot get below than the sample size recommended and get more in the other schools. You cannot replace that from other schools. You have to stick to the minimum sample size recommended based on your calculation. So that's all, and I hope you have learned something from this video.